We're working at 8.2, hopefully learning probability. Does anybody have any homework questions? Oh, a bunch of homework questions. What is yours?
On 8.2, the landscape page.
Which landscape?
8.
So we're in 8.2, so we maybe are not quite ready for these. Let's see. Okay, we're going to be doing this one actually in class. Okay, so if you still don't get it on Friday, then we'll do it on Friday, okay?
Okay. Could we do it for the second part?
Okay, so I have to make this bigger. I sure can't see it this size. We have a game at a carnival with 86 rubber ducks, so you probably have a different number of rubber ducks, okay, that are numbered from 1 to 86 with the numbers written on their undersides so they can't be seen. Who played this game as a child? I remember playing this game. Yeah, okay. To play, you select a duck and see what number it has. If the number is less than 60, you win a consolation prize. If the number is at least 60 but less than or equal to 70, you win a stuffed duck. If the number is greater than 70, you win a giant stuffed banana. So the whole probability that we've been looking at so far, we have a formula for. Let's see if I can get this on the screen along with the document camera. So the formula that we had was that the probability of an event occurring is the number of different outcomes in the event divided by the number of equally likely outcomes. So what is the number of equally likely outcomes on this problem? So there's 86 ducks on my problem. So for mine, the denominator is 86. Then you need to get a number between 60 and 70 to get a stuffed duck. So how many numbers are there between 60 and 70, including the 60 and the 70? Did anybody count those up? There's actually 11. So you just count them on your fingers if you're like me, 60, 61, 62, 63, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so, 70. So we're going to 70, so there's 11 numbers. Okay, so there's 11 numbers, so mine would be whatever 11 divided by 86 is. So remember the rule. The rule is to look at the 6th digit, and if the 6th digit is 5 or above, round the 5th digit up. So mine would be 0.12791. What is the probability you don't win a duck or banana? So if you don't win a duck or a banana, it's because you got 1 through 59. So I'd have 59 chances not to win a duck or a banana. So 59 divided by 86 for mine, you might have a different number of ducks. So 0.68605, because the number 6 is 5 or above. So I'm going to round over here to 5. Do you have other questions?
For landscape 2, the same section.
So we have a dime and a penny, and we flip them both noting whether each coin lands heads up or tails up. So we write all the possible outcomes, and that E be the event that you get at least one head. So list all the outcomes that give E. What is the probability that E occurs? Okay, so we're flipping a dime and a penny and listing all the possible outcomes. Okay. So the dime could be heads, and the penny could be heads. Or the dime could be heads, and the penny could be tails. Or the dime could be tails, and the penny could be heads. Or the dime could be tails, and the penny could be tails. So with 2 coins, those are the possible outcomes that we have. And then we need to look at the probability that we get at least one head. So there's 4 possible outcomes altogether, so that's the denominator, and the probability that at least one is a head, 1, 2, 3. That would be 3 out of them. Only the tail did not have one of the heads. So I don't know if we have to write that as 3/4 or as points.
Put it in as an or.
Pardon?
It works if you put it that way.
3/4?
Yeah.
Okay, thank you. Any other questions? Well, let's continue to look at probability then in 8.2. So our main ideas in 8.2 are the definition of probability that we wrote last class. The probability of an event E occurring is the number of different outcomes in the event divided by the total number of equally likely outcomes. And that's how we'll be approaching probability. We'll be looking to find all the different possible outcomes and then picking out the ones that are in the event that we are looking at. We did some experiments, and that was to show the law of large numbers in action. If an experiment is repeated a large number of times, then the relative frequency of a particular outcome will tend to be close to the probability of that particular outcome. So the experiment gets closer and closer to the probability that we predict, if we predicted the probability correctly, for one thing, and if we do enough of the experiment. So I had a question for you. We're not going to do 8.3, but I wanted to ask you a question out of 8.3. If you flip a coin 10 times and it comes up heads 10 times in a row, and it's a fair coin, what's the probability on the 11th toss that you get heads? So you flip a coin 10 times, comes up heads, it's a fair coin, there's nothing wrong with it. What's the probability that the 11th toss is heads? Anybody? What would it be if you didn't have 10 heads tossed before that?
1/2.
Yeah, 1/2. So the probability of flipping a coin and getting heads is 1/2. Well, if you flip a coin 11 times and the first 10 are still heads, the probability of the 11th time is also heads. So here we have an experiment done in 8.3 where a coin is flipped 1,000,000 times, actually more than 1,000,000 times, in 3 different trials. And then the author keeps track of those 1,000,000 flips, how many have, where did 10 heads come up in a row? And on the 1,000 times that happened, the 11th time there were 495 tails and 515 heads. So you see it's pretty close to 50-50. It's a little bit off because probability is a prediction. It's not like stamped solid on wood that that's what's going to happen. It's a prediction of what's likely to happen. And here you see the same probability, about half and half, half and half. So when we look at probability, we get a number. Okay, so you can express the number as a decimal or as a fraction, but the probability becomes a number between 1 and 0. What does it mean if your probability comes out to be 0?
It's not likely to happen.
So it's actually impossible. It's not going to happen. The exception to that is if you're working with an infinitely large outcome possibilities. If you have infinite outcomes possible, then something that we would call impossible in a finite set could actually happen, but we're not looking at infinite sets. Same thing with 1. What does it mean if your probability is 1?
It happens every time.
Yeah. So it's going to happen. If your probability is 1, it's going to happen. If your probability is 0, it's not going to happen. So when we have a probability of 0.75, that's closer to 1. So that's very likely to happen. Well, I'd like to make sure you can do some basic probabilities. So let me give you a few questions that are similar to those you'd run into on a quiz. So a boy has a bag with jelly beans. Three are red, 5 are green, and 6 are yellow. Boy has a bag with jelly beans. 3 are red, 5 are green, and 6 is yellow. The question I have then, what is the probability what is the probability of drawing A, a red, B, a green or a red, C, a yellow, D, not red, E, a blue. So we're always putting the jelly beans back, so we don't have to worry about the one that's missing. All the jelly beans are in the bag after every draw. You just put the jelly bean back. So we'll go ahead and calculate some of these probabilities, and then I'll let you calculate some on your own. So first, we have to figure out all the possible outcomes when you pull out a jelly bean. Okay, so you pull out a jelly bean, you're going to have 3 reds to pick from, 5 greens, or 6 yellows. So all the ones that you could pick altogether, there's 14 jelly beans. So when we're picking out a jelly bean, the total number of equally likely outcomes is 14. There's 14 equally likely outcomes that we could pick from. And then we just have to put on the top of the fraction the number of different outcomes in that particular situation. So for red, there's 3 red. So you'd answer 3 divided by 14 as a fraction, or you could put that as a decimal. So I'd like you to figure out the other probabilities. Okay, so figure out how many outcomes would be green or red out of those 14, and so on. I'll come around and see how you're doing, and if you're stuck, will you please raise your hand? I don't want you to leave class without being able to do these fairly straightforward probability problems. Okay, if you answered as a decimal, I don't know, because I don't have mine as a decimal. So I did not get around to everybody's. The green or red, there's 3 reds and 5 greens, so altogether that's 8 out of 14. The yellows, there's 6, so 6 out of 14. Not red, that would mean picking a green or a yellow. So there's 5 plus 6 or 11 that are not red. So 11 chances out of all of the 14 to get one that's not red. And somebody said it was blue, there's 0. 0 out of 14 chances, because there are no blue. So you can take your fractions and reduce them if you want to, or you could write them as decimals, or you can leave them as fractions, whichever you like in this class. Does anybody have any questions on any of those? Does anybody want to try another one? Okay, if those didn't work out for you, please see me after class, okay? Or you could see Jake. There's study group meeting from 2 to 3 today, so it's a good idea to get ready for your 3rd quiz by going to the study group as often as you can. Another type of typical problem I would ask on a quiz is about dice. We're going to look at rolling 2 dice, and we're actually going to make the possible outcomes. So we're going to simulate that by making a little chart, and this would be something I would ask you to make on a quiz and then to use to answer questions. So let's make sure you know how to do this. Use 2 different color writing implements if you have them. Okay, so I'm going to use black and purple, unless my purple doesn't show up. Sometimes it doesn't show up. So I'm going to roll a dice, and I could get a 1 with the first dice, and I could get a 1 with the second dice. Or I could get a 1 with the first dice, and I could get a 2 with the second dice. Or I could get a 1 with the first dice and a 3 with the second dice. These are just regular 6-sided dice. So I'm going to list all the options that I could get with a black 1, and then what other options I could get with a purple. So I could get a black 1 with a purple 5, or a black 1 with a purple 6. Then I'll go through and do the same thing with a black 2. So if I had a black 2, then I could get a purple 1, 2, 3, 4, 5, or 6. I'll write all the 2's down first, so that will be a little faster. So I could have a black 2 with a purple 1, 2, 3, 4, 5, 6. I could get a black 3 or black 4. Or 5. Or a 6. So this is the chart that I'll use to represent the different ways I could throw 2 dice. So when you throw the 2 dice, we're looking at all the different possible outcomes so we can see the probability of different outcomes. So first we want to see all the possible outcomes. So when you roll the dice, the black 6 and the purple 5 is 11, and the black 5 and the purple 6 is 11, but it's 2 different ways of getting the 11. So you have to list both of them, and that's why we use 2 different writing implements so you can see that there's 2 different ways to get that 11. Well, let me put some probability questions down to go with this now. So what is the probability of rolling with 2 dice? A total of 5. B, doubles. C, a total of 10 or more. D, a total of 2 or of 12. E, a total of 3. And we'll do one more. Does anybody else play Catan? Who plays Catan? Anybody? Oh, Catan players. Okay, well, we have to put a total of 7 down in case there's any Catan players watching online. So we're looking back at our definition of probability and using it here. We need the total number of equally likely outcomes, and then we'll pick out of that the number of different outcomes in the event that is listed. So what is the total number of equally likely outcomes here? You're rolling 2 dice. How many different outcomes are possible? How many combinations of those 2 dice? You just listed them all. Good, 36. So 36 equally likely outcomes. So 36 will go in the bottom of all of our fractions. And then in the top of the fraction, we just have to count out how many are in the event that we talked about. So we talked about a total of 5. So look at your dice and see where there's a total of 5. So here's one with a 4 and a 1. Here's another one with 3 and 2. Here's one with the 2 black this time and the 3 purple. The other one was the black 3 and the purple 2. So this is a different 2, 3 than the 3, 2. And then the 1 and the 4. So there's 1, 2, 3, 4 different ways to throw a 5. So 4 out of 36. or 436 it would be the probability. So again, you can leave that as 436. You can reduce it, or you can write it as a decimal. Decimals are nice if you're comparing probabilities. Let's take a look at doubles. So doubles means you get the two dice the same. So there's a 1 and a 1, 2 and a 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So there were 6 ways to get doubles out of all the 36 different ways to roll 2 dice. So that's how we're looking at probability when we're rolling 2 dice. We're going to have 36 for the denominator, and you just have to count up how many different ways there are to do the event that we're discussing. So I'll come around and see how you're doing. You go ahead and work on these, and if you're stuck, please raise your hand, okay? I don't see that well, so a lot of times I'm looking at your papers and I'm just not seeing as well as I would like. So like yours are done again?
Yeah, I'm already done.
Okay.
What was that one? I don't think that one might be 7. Oh, duh.
And you're already done too? Well, okay. I got the same thing. Except I didn't write down the 3. Yeah, that's right. And did you make a chart? Oh yeah, that one's okay too. Anybody have any questions? So a total of 10 or more, that'd be the 6 and 4, 5 and 5, 4 and 6, 5 and 6, 6 and 5, 6 and 6. So 1, 2, 3, 4, 5, 6. 6 out of 36. A 2 you can only use with the 1 and the 1, a 12 with the 6 and the 6, so that's 2 out of 12. A total of 3, there's only 2 as well, the 2 and the 1, or the black 1 and the purple 2. Oops, I put 12 instead of 36 there. And 7, 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. 1, 2, 3, 4, 5, 6. What is the total you're most likely to roll when you roll 2 dice? What is the total you're most likely to roll? So you can get anything from 2 to 12. What are you most likely to get? 2, you have a chance of 1 in 36. So that'd be least likely. Least likely, yeah. What's the most likely? What do you have the most chances to get? Yeah, 7. So most ways to roll 7. So a lot of games depend on that. A lot of dice games. So that's your basic probability, and I wanted to make sure you know how to do that. We're going to look at some questions that are a little trickier first. A little trickier next. Do you have any questions though? If these last couple problems didn't come out for you, make sure you get some help. Here's another example that's harder. A student flips 2 coins and covers them up. The student flips 2 coins and covers them up. If at least one coin is heads, the student announces at least one coin is a head. What is the probability that there are two heads? What is the probability that there are two heads? I thought about using the law of large numbers and having you work this out by having all of you flip two coins and have this experiment. But I don't think we'll take the time for that. So a student flips two coins and covers them up. If at least one coin is a head, the student says, at least one coin is a head. What is the probability that there are two heads? So go ahead and write out the possible outcomes when at least one coin is a head. So go ahead and see if you can list the possible outcomes. At least one coin is a head. Anybody want to tell what the possible outcomes are? Does your group have it? Do you have the possible outcomes?
There's three possible outcomes.
Good. What are they?
You could get a tail and then a head, two heads, or then a head and then a tail.
Perfect. Okay, so you could have one is a tail, one's a head, or you could have two heads, or you could have the head first and then the tail. Okay. Okay, great. So with that in mind, can you go ahead and write out what the probability is that there are two heads? Anybody have it? What? Two heads.
Oh, 1/3.
Perfect. Yep, 1/3. So probability there is 1/3. So not having the tail as an option changed the outcome there, okay? So you have to look at your new probability space with no tail as an option, just the options that we had. Three possible outcomes, one of those is two heads. Now we're going to look at some of the harder problems that we did in 8.1, but hopefully you'll be able to do them now that you know a little more about probability. Remember the class scenario outcome from 8.1. We had situation A, I have two children, at least one is a boy. Situation A was I have two children, at least one is a boy. Situation B, I have two children, the oldest is a boy. I have two children, the oldest is a boy. Then the question is, what is the probability that both are boys? So probability for A and probability for B. But now that you know how to write out the different the different possible outcomes, can you go ahead and list the possible outcomes for A? and for B. So write down the possible outcomes for I have 2 children, at least one is a boy. And then write down the possible outcomes for I have 2 children, the oldest is a boy. So what are the possible outcomes for I have 2 children, at least one is a boy? Pardon?
1 out of 2.
So that's, you're going right to probability, and I'm asking you to do like BG, G, G, whatever you would think. Okay, so what possible outcomes that way? So
I put GB and BG.
So GB, and what was the other one? BG?
Yeah, and CB.
Anybody have any others? So here the oldest is a girl, then a boy. And here the oldest is a boy, then a girl.
2 boys.
2 boys. Okay. So that's the other outcome. So here's at least one is a boy. And for B, I have 2 children. The oldest is a boy. What are the possible outcomes there?
AB or BB.
Good. BB or BG. So boy comes first there. Okay, now that you know all the possible outcomes, now you can write the probability that both are boys for A and the probability that both are boys for B. What is the probability that both are boys for A?
1/3.
1 out of 3, because it is these 3 equally likely outcomes. Okay, and for B? 1/2. Yeah. 2 equally likely outcomes. So the when we could focus on all the possible outcomes instead of going right to probability, then we can figure out that probability. The other scenario we had was the Price is Right. So let's see if that makes more sense now that we've talked about probability. So we're in 8.2, but we're looking back to questions raised in 8.1. And in the Price is Right, there were 3 doors. Behind those 3 doors were either a Cadillac or a mule. So there's 1 Cadillac and 2 mules. So the Cadillac, I'm just going to write car, that's shorter. The car could be behind door number 1. Or the car could be behind door number 2. Or the car could be behind door number 3. Now Warren Peace picked, that was the contestant, Warren Peace picked door number 3. So once Warren Peace picked door number 3, Monty opened one of the doors with a mule, and you simulated that when you did that with the deck of cards. So we opened one of the doors with a mule. So in this situation, Monty would open door 2, and that is an option that's off the table now. In this situation, Monty would open door number 1, and that situation is off the table. In this situation, Monty could open either door, so I'll just take door number 2 out. So the X's are gone. Those are not an option anymore for Warren Peace. So Warren Peace has to decide to stay or switch. If Warren stays, then in this situation, he gets a mule. In this situation, he gets a mule. And in this situation, he gets a card. So of those three situations, one of them is the card. So if he stays with what he has, he'll have a 1 in 3 chance of getting that card. Now look if he switches. If he switches in each of those three situations, how many chances does he have to win the card then? If he switches in this situation, he gets a card. If he switches in this situation, he gets a card. If he switches in this situation, he gets a mule. So there's 2 in 3 chances of winning if he switches, because then he'll be getting those 2 in 3 chances that were mules before. Well, those are switched out and they're gone, and now those 2 are switched out to be cars. The other situation we had was the birthday situation. Before we go to that, though, I wanted to show you a different one. Okay. Does anybody have any questions about the cars or the reunion scenarios? Okay, here I have 3 pieces of cardboard. One has an X on both sides, one has an O on both sides, one has an O on one side and an X on the other. So I'm going to shuffle those. One has an O on both sides, one has an X on both sides, and one has an O and an X on both sides. So I'm going to shuffle them and I'm going to pick one out. There. So an X is showing on the card that I put up there. And my question is, what is the probability that the other side of that card is an X? Let's try and make sure you can't see these ones. Okay. What is the probability that the other side of that card is an X?
It's 1 in 3, right?
So you're thinking there's 3 cards.
You're right, 1 and 2.
Okay, so one way is to think there's 3 cards, and the one with XX, there's 1 out of 3. And 1 and 2 is that, okay, it's either O or X, and there's 3 of each. So I can see where you're thinking both of those. Any other ideas? Okay, let's see what it is here. We're seeing an X. It could have an X on the other side, or we could have the X with the O on the other side. The O with the O on the other side is definitely not there. Okay, so it's one of these 3. So the denominator is 3. Okay, because there's the 3 outcomes we're looking at is where there's an X on the side we're looking at. Now, of those 3, if you flip it, how many will give you an X? So we either have the X on one side of one card, or the X on the other side of that same card, or we have the X that has an O on the other side. So it's one of these 3, that's the denominator. Of those 3, how many will have an X on the other side when you flip it? 2, because we could be looking at this one and have an X on the other side, or this one and have an X on the other side. But if we're looking at this one, we're not going to have an X on the other side. So there's 2 out of 3. This one was the one with the X on the other side. That's not very straightforward. That's one of the harder ones. I've had a lot of discussion with other colleagues about that one. Well, I'd like us to look at the birthday scenario one as well. So you need 40 people in a room to have a 0.9 probability of a shared birthday. Well, we don't start right with birthdays because that's hard. We start with dice. We're going to start with what is the probability of rolling a pair with 5 dice. What is the probability of rolling a pair with 5 dice? So does anybody play Yahtzee? Who's played Yahtzee? Okay, that's what you play when you go to the cabin and there's no internet. Okay, all right. So play Yahtzee. You roll 5 dice. You're hoping for a pair most of the time, at least to start. Even that, we don't start off with 5. We start with 2. So you figured out the probability of rolling a pair of dice earlier in the class. Does anyone remember what it is? Good, 6 out of 36. I'm going to put these in decimals so we can use calculator here. Now it turns out that for calculating these probabilities, it's actually easier to calculate the probability of not having a pair. So the probability of not a pair is equal to 1 minus the probability of a pair. That's true for any event. The probability of an event happening is 1 minus the probability of the event not happening. Or I said it the other way around. The probability of an event not happening is 1 minus the probability of the event happening. Here's your pair of dice written with actual dice-looking characters instead of the numbers that we use. So you counted off the pairs. How many of those are not pairs? Good, yeah, 30. So you have 36 altogether, and you're either a pair or you're not a pair. And so that's why the probability of something not happening is 1 minus the probability of something happening. So the probability of not a pair is 30 out of 36, which is 1 minus 6 out of 36. So what is 30 out of 36? A decimal. 0.833. Well, now we're going to look at 3 dice. And we're going to look at it as the opposite. We're going to find the probability of a pair by taking 1 minus the probability of no pair. So we're going to find the probability of a pair with 3 dice by looking at 1 minus the probability of no pair. Now your author has a picture for that. So when we were looking at the table with the 2 dice, we had all the possible combinations of red with all the possible combinations of green. Now there's one more dice in there. So here we have a layer for each of the yellow dice possibilities. So here's the green one with the red one, and the top layer is with a yellow one. And then you could have the green one and the red one and go down a layer with the yellow 2. Or you could have the green one and the red one and go down a layer with the yellow 3. So our outcome with 2 dice was the 6 times 6 possibilities. 6 times 6 is 36. How many outcomes are possible with 3 dice?
116.
Good, 216. 6 times 6 times 6. Okay, so total possible outcomes will be 216. But I'm going to think of it as 6 times 6 times 6. Well, now we're looking at the probability that there was no pair. So let's again go back to when we had 2 dice. When you have 2 dice and you're looking for ones that are not pairs, you say, okay, if the red dice is a 1, then the green dice can't be a 1. The green dice can be 2, 3, 4, 5, or 6. So the green dice can be anything but a 1 if the red dice is a 1. If the red dice is a 2, then there's 5 different numbers that the green dice can be, any other number but 2. Same thing with 3. If the red dice is a 3, then there's 5 other numbers the green dice could be, and that's how we got 30. We had 6 different red dice possibilities, and of those, the green dice couldn't be any of those 6. We have a similar process here. We say, whatever that red dice is, the green dice has to be 5 other possibilities. It can't be what the red dice is. And the yellow dice has to be 4 other possibilities. So we put this in the calculator and see what we get. So I didn't round properly there, so we'll just leave it. I'll round it here. So the probability of not getting a pair is 0.56 with 3 dice, and that means the probability of getting a pair is 1 minus 0.56 or 0.44. And we can do that with 4 dice as well. Same thing. But now you have 4 dice, so you have 6 more outcomes possible. And as you're looking for numbers that aren't pairs, you have 6 times 4, 5 times 4 times 3. And we do the same thing with 5 dice. So I figured these out in an earlier class, so I'll just write down the numbers. So the probability of getting a pair with 5 dice is 1 minus the probability of not getting a pair, and that comes out to 0.907. Well, we're going to do the same thing with birthdays, but it'll be a bigger space. It'll be 366 days to look at then. I'll see you on Friday, and we'll figure that out on Friday.